In the first part of this video, I'm going to look at how to edit the number of decimal places shown in Logger Pro. Everything I do with this could also be done with the Vernier graphical analysis app. It'll have similar options. All right, so this is an example of me tracking the position of my buggy over time as it moves at a near constant rate across the desk here. I click the points to locate its position, and Logger Pro turned those into a data table for me. Now, the issue I ran into here is Logger Pro is thinking that I'm able to click to what looks to be the like 100 or 1000th of a meter, like way too specific. Like looking at this, maybe I'm clicking to the nearest 0.1 centimeters accurately, which would only be 3 decimals here. So this data is way more precise than I could actually be doing here with my measurements. So I want to trim this down, and here's how I'm going to do that. I'm going to double click on the title of the column. I'm going to go to options. And here I can choose displayed precision. I'm going to go with decimal places. And I can pick the amount of decimal places that I want. So if I said, okay, I can maybe click to the nearest centimeter. That would be 2 decimals because there's 100 centimeters in a meter. So you'll see, and you can rewind the video if you want to look at what this looked like before. I've drastically cut down the number of decimal places. I've made my precision, you could technically say worse, but in this case, my precision is now more accurate to what I actually was able to measure to. So that's important. Even though I made it worse, I am making it better in that it's actually what I was able to do. So I could do similar things for time and these other quantities if I felt that they were also being reported too specifically. All right. Second thing, so that's precision in my data table. That's how I can change that. Now I want to talk about precision in my equation. And so this is going to involve significant figure rules. So you might want to watch a separate video on that first if you need a refresher on significant figures. There's loads on YouTube. But I have a slope given to me by my graphing software, and I have an intercept. And those are each given to a certain level of precision here and here. And the question is, what should I report those to in my lab report? Because this is just the software spitting out numbers. Just like here, it spit out a bunch of numbers that had too many decimals, that were too precise for me. I need to look at this and do the same sort of thing and figure out, okay, how much should I cut down here? And it's going to be a different sort of idea for the slope versus the intercept. So for the slope, I'm going to want to use my significant figure rules because slope is determined by calculating the rise over the run. So that's a calculation. When we do a calculation, when we do like a multiplication or division, then we use significant figure rules. So in the case of my slope, I want to look at my rise significant figures and my runs significant figures. So I'm just using my data here. My rise is my x position, which looking at this, I've measured to 2 significant digits because this first 0 is not significant. My run is time, and it looks like this time is being measured to 4 significant digits in most cases here. Multiplication rules say if I'm doing rise divided by run, I base my result on my measurement with the lower number of significant figures. So position was 2. So that's what I'm going to go with. So my slope, I'm only going to report to 2 significant digits. So that would be 0.43 meters per second. I'm going to cut off this 5 in this. I guess you could round this up. 0.44 meters per second. So I'm going to cut it down to just 2 significant digits because my rise variable only had 2 significant digits, while my run had more. So that's how I would do the slope. For the intercept is a measurement of your y variable when your x variable is 0. So in this case, my intercept is a measurement of my initial position. Right now it's saying 0.1808 meters. But if I look at my data table, I said I could only report my positions to 2 decimal places. So if the things I actually recorded were only to 2 decimal places, there's no way that my estimate from my best fit line can be more precise than that. So I would cut this down to match the number of decimal places here. So this would be 0.18 meters, because then it's to the same precision. So I'm not using significant figures here. I'm not counting the number of things. I'm just counting where I am decimal place wise. It's a coincidence that this has 2 significant figures and also 2 decimals. So this would be 0.18 meters. So my final equation would read x equals 0.44 meters per second t plus 0.18 meters. Okay, cool. So that's the first part of the video. If that's all you needed, you can go on with your life. The second part of this video, we're going to look at how do we analyze a relationship that is not linear. So relationship, we've graphed it, and we got something that wasn't a line. Let's look at that. So here I have a logger profile. This is some made up data. We could pretend maybe it's time and position. So maybe it's a cart going down a ramp or something like that. And we're getting that it is not a line from position versus time. The position has a curve to it. Spoilers, we know this is quadratic from our work with kinematics, but let's say we weren't sure. We looked at this, we're like, oh, this isn't a line. What kind of relationship do I have? I could go on Schoology. I could find in my Schoology this graphing method summary sheet. It's called like graphing relationships as the Schoology file. And this has a bunch of different ways variables are related that we see often in nature. So this is not every single kind of relationship, but it's ones that show up a lot. And I try to look for which one matches my graph. And I'd say, oh, this one looks like it might match. And it tells me y is proportional to the square of x. So that's an equation that looks something like this. And it's going to tell me what I need to do to linearize the graph, to turn it into a line so I can get an equation from it. You'll see all of these end up looking like y equals mx plus b, but we kind of change what the x is or what the y is. So it tells me I need to graph my y variable versus my x variable squared. So if we go back to Logger Pro, I want to graph my y variable versus my x variable squared. So my y variable, position, I want to graph it versus my x variable, time. But instead of doing position versus time, I want to graph position versus time squared. So here's how I'm going to do that. Go to data. And again, in Vernier graphical analysis, you are able to do all these steps as well. I'm going to go to new calculate. I'm going to choose calculated column because it's going to save me some time. I want it to be time squared. So I could call that t squared. Units would be seconds squared. And how do I get that? Well, I take my time variable. So I'm clicking variables here, time. And I'm going to tell Logger Pro I want you to square it. So that's what this caret 2 means, square. And we click done. And you'll see it's going to create for me a new column. And that column is my times squared. So, I mean, if you had a calculator, you could check that 8.899 here is this value squared. All right, and then I can just go to the bottom here, and I can switch it from doing time to time squared. And I'll see, hey, this is a line now. I know how to get an equation for a line. Boom, linear fit. Now I have an equation for this line. And it's in y equals mx plus b form. The only thing I have to remember when plugging in my actual name, so instead of x on the left here, I'm going to call it position. And this is going to be m, and this, my variable, my horizontal axis variable here is going to be time squared. So I would say position equals 1.9 whatever. I'd have to do some sig fig rules there. Meters per second squared. I'm going to put time though. I'd put time squared plus negative 2.4 meters. And now I have an equation, and that equation would read position equals 1.985 time squared plus negative 2.441 meters. Again, that's without me cutting down these digits as we talked about earlier in this video. Cool. If I had done the inverse, I would do y equals m 1 over time, and then plus, my b value. So that's linearizing the graph. It allows us to take a graph that's not linear, like this position versus time graph here. Let's scale it again so we can see that. Now we might not know how to get an equation for. Yes, we could cheat by using a curve fit, but let's say we didn't know how to get equations for things that aren't linear. We could take that curve and we can make it give us this linear graph instead. Now this doesn't mean position and time are linear. It means position and time squared are linear. Position and time is still, if I go back to that, is still a quadratic. That hasn't changed, but now we can get an equation for this quadratic. All right, peace.